ask me how I knew my true love was true. I of course replied, something here inside cannot be denied.
The next section is 3.5. It's unrelated rates. And this, my friends, is a very hard section. You might want to put some of these all around the title to remind yourself that this is difficult. Don't get upset if you have troubles with this section. I would say in the whole course there's probably, I don't know, 4 sections that I'm going to say this, give the superstar designation to, and this is one of them. Related rates is very difficult. So these are word problems, related rates problems, and here's a few things about them. What's going to happen is we're going to be given the rate of change of one quantity, and we must find the rate of change of a related quantity. And we're always going to use implicit differentiation in terms of time. Okay, it's always going to be in terms of time. Now, the steps, I found this acronym, I didn't make it up, DREADS. It's pretty good. It's not spelt right, but DREADS. Everyone dreads related rate problems. So here are the steps. Draw a picture. Rates, you're going to put down the rates. Label any quantities that are functions of time. Equation, you're going to make up an equation that relates the two quantities. Differentiate, and as we said, it's going to be implicit differentiation. Substitute specific information and solve for the unknown. And this is one of the things that gets people into trouble a lot of time. You must do this substitution step. You must do it last. In fact, you're going to do all these steps in order, so it should be easy to remember to do it last. But people try to do the substitution step too early often because you're so used to always putting all the information in the question into your drawing, but you don't want to actually do that when it comes to related rates. Okay, let's go through a few of these questions and we'll see how we do. So the first one says, a spherical snowball is melting in such a way that its volume is decreasing at a rate of 1 centimeter cubed per minute. At what rate is the radius decreasing when the radius is 5 centimeters? Okay, so remember, all these questions, they're looking at two things where we're given the rate of change of one quantity and must find the rate of change of another one. So what are the two quantities, first of all? Well, the two things we're talking about in this question are volume, and it says it's decreasing at a rate so we're given the rate of that one. That's the one we're given. The one we're not given is the radius. This is the other one, the other quantity, and this one's also decreasing, but we don't know at what rate it's decreasing. Okay, so this fits in perfectly with the related rate question. We're given the rate of change of one quantity. In this case, it's volume, and we must find the rate of change of the related quantity. In this case, it's radius. I'm just going to go back up here for a second. I think I forgot to write something. When I say you're always going to use implicit differentiation in terms of time, what that means it's going to look like. So therefore, you're going to end up with something that looks like dA dt, right? This could be the change in area compared to the change in time, or maybe it's going to be dV dt. Maybe that's change in volume. That sounds like one we're going to use in the question down below. Maybe it's dN, maybe it's the number of individuals over time, or maybe it's dP, whether that's pressure or I don't know what else could P stand for, but it's going to be something like this. You're always going to have this dt on the bottom because it's always going to be in terms of time. Okay, sorry for missing that. Okay, so back to this question. We have our snowball. Maybe I'll just draw it. I'm just going to draw it as a circle, even though you know it's like a three-dimensional ball here. And it's melting in such a way that its volume is decreasing at a rate of 1 centimeter cubed per minute. So what we know is that, I don't know how you draw this. I guess you could draw like some arrows inwards to show it's melting, it's getting smaller, and we know the rate at which that's happening. We know that dV dt, in other words, the rate at which the volume is changing, is equal to 1 centimeter cubed per minute. Since it's decreasing though, let's make it -1. If you put 1, it's going to make it, that would be the snowball getting bigger. So we're going to put -1 centimeters cubed per minute. I tend to leave off my units when I draw these things just to make it simpler so I don't get confused with all the units and everything. But you're welcome to put the units there if you want. What we want to know is the rate at which the radius is decreasing. So what we want to know is dr dt. That's what we want to know. But we don't know it, right? So I'll put a question mark here. Now, in this case, we've drawn the picture, we've labeled the rates. Here's the one we know, here's the one we want to know. The next thing we want to do is we're going to find an equation that relates the two quantities. So we need an equation that relates the volume of a sphere, the volume of the sphere, and the radius. Well, in this case, it's pretty easy because there's a formula that relates volume of a sphere and radius. It's the volume of a sphere formula, which is V equals 4/3 pi r cubed. Right, so we now have a formula that relates V and R, which are the two variables we're interested in this question. So now we're going to differentiate. We're going to use implicit differentiation, and we're going to do it in terms of time. So on the left hand side here, what we're going to do is we're going to do dv dt. Why is it dv dt? Well, if you want, you can think of it as implicit differentiation here, because this is like v to the first power. And whenever you have something to the first power, what's the derivative of it? So for example, if I had y equals x, what's the derivative of that? What's y prime? I'll make it y prime. Well, y prime is 1. So that's what's happening here. We're taking the derivative of v, which is just 1. I can put the 1 there if you want. And then, because we're doing this in terms of t though, there's no t here, this is a v, we have to write v prime or dv dt. I encourage you to use dv dt to remind yourself it has to do with time. Okay, so this is just implicit differentiation. We don't need that one though. Okay, equals. Now, the only variable we have here that's unknown is the r. So again, we're going to use implicit differentiation in terms of time. So yes, we are going to do the power rule. The 3 is going to come down, and it's going to multiply the 4/3. Should I draw that? Might as well. So we have 3 times 4/3 pi, and the r cubed is now going to become r squared. But remember, we're not doing this in terms of r, so we now have to do implicit differentiation, which means we have to add on to this dr dt. Okay, this is always going to be the case. When you're taking the derivative, it's always going to be dv dt, dr dt, dp dt, whatever. Okay, so dv dt equals, well, these cancel, so I'm left with 4 pi r squared dr dt. Great, we've done the derivative. Now what we're going to do is we're going to substitute in the stuff we know. So let's see what we know. Do we know dv dt? Yeah, we do, right here. dv dt equals -1. 4 pi. Do we know r? Yeah, we're interested at the rate that the radius is decreasing when the radius is 5 centimeters. That's the specific radius we're interested in. So we're going to plug 5 in here. So we got 5 squared. And then dr dt. Do we know that? No, we don't. That's what we're trying to find. We're trying to find the rate at which the radius is decreasing. So all we have to do is simplify this, isolate the dr dt, and we'll have an answer. So -1 equals 5 squared is 25 times 4 is 100 pi dr dt. Divide both sides by 100 pi. You're going to end up with dr dt equals -1 over 100 pi. Or if you want, if that's hard to picture, if you take your calculator and divide 1 divided by 100 pi, you're going to end up with -0.003. Of course, that's a rounded answer. Now, what are our units? Well, it says right here, the units, the rate is centimeters cubed per minute, which makes sense, right? Centimeters cubed is the change in the volume, and minute is the time. The bottom one should always be time, since we're always going to be taking our derivative in terms of time. So this is our answer. When the radius of the snowball is 5 centimeters in size, at exactly that point, this is the rate at which the snowball's volume is decreasing. If we weren't interested in 5 centimeters, if we were actually interested in when it was 2 centimeters, we'd do the same thing, except we would have plugged 2 in here instead of 5. Okay, so that's how the substitution works. Notice you do that at the end. Don't plug that 5 in at the start. A lot of people do that. Like when they find this formula right here, they go ahead and plug 5 in here right now before they take the derivative, and everything goes wrong. You do not want to do that. Okay, a man starts walking north at a speed of 1.5 meters per second, and a woman starts at the same point P at the same time, that's a bit awkward, walking west at a speed of 2 meters per second. At what rate is the distance between the man and the woman increasing 1 minute later? So let's picture this. We have our point P, and we have a man walking north. Let's call that direction y, since it's kind of an up-down direction, right? So we know that rate that he's moving, dy dt, we know it is 1.5 meters per second. Now, the other person is walking west, northeast, southwest, this way, and they're going 2 meters per second. So let's call this dx dt. This is a rate, so is 2. And what we know is at what rate, or what we want to know, at what rate is the distance between the man and the woman increasing? So we want to know this rate here, the rate of the distance they are apart from each other. Well, why don't we call this z, which means what we're interested in is dz dt. That's what we want to know. How fast is that changing, that amount right there? So basically what we want here is we want to find an equation now. We've already drawn our picture, we've put our rates, we want an equation that relates these three things in this point. Oh boy, that sounds hard because we have three things. But come on, this isn't too tough to think of what you're going to use. This is a right angle triangle. We're talking about the sides. You know what you're going to use, right? You're going to use good old x squared plus y squared equals z squared. Pythagorean Theorem. So this is our x, this is our y, this is our z. And we're going to take the derivative of that. So we're going to go 2x, but remember, we're not doing this derivative in terms of x, we're doing it in terms of t. So what do we have to add after we do the 2x? dx dt. This is going to be ever constant with your related rates. Plus, okay, we take the derivative of this, which is 2y. But it's in terms of t, so implicit differentiation tells us we got to go dy dt. Then we do the derivative of this, 2z, but then dz dt. Okay, great. This is our derivative. Now we're ready to plug in. So we have 2x. Well, we don't know x. I'm just going to leave a blank here for now. We don't know x. dx dt, we do know. It's 2. Plus 2 times y, but we don't know y. But dy dt we do. We know it's 1.5. And then 2 again, z, but we don't know z. And then dz dt, we don't know that either, so we got dz dt. We've got a lot of unknowns. Okay, we actually do know one other thing, right? We want to know at what rate is the distance between the man and the woman increasing 1 minute later. This is our key. What I would do now is I would draw another triangle, and this time I'm going to put some different information on it. So we still have our point P here. Let's see, 1 minute later. Well, if this guy's going 1.5 meters per second, then how far has he gone after 1 minute? We'd have to go 1.5 times 60, which is 90 meters. So this distance from here to here is 90 meters. How far has this one gone? Well, they're going 2 meters per second, so 2 times 60 is 120 meters. So right away you can see that you have your y amount, right? There's the y right here. This is y equals 90 meters, so I can plug that in right here, 90. You have your x amount, x equals 120, so I can put that in here. We can't have two unknowns, so it would be nice if we knew the z. We can figure out the z. If our x is 120 and our y is 90, what can we do to figure out z? Same thing, you can use the Pythagorean Theorem. So to do the Pythagorean Theorem here, you would go 120 squared plus 90 squared, and then you would take the square root, right? And if you do all that, you will end up getting 150. So that's how much our z is 150. Great, now we only have one unknown left, the dz dt, which is the rate at which this distance right here is changing. That's exactly what we want to know. So we can just go ahead and solve. We'll be done. 2 times 120 is 480. 2 times 1.5 is 3, times 90 is 270. 2 times 150 is 300, and we still have the dz dt. Add these together, you get 750 equals 300 dz dt. All you have to do now is divide by 300, so you get dz dt equals 750 over 300. Let's knock off a 0, and let's divide them both by 5. So 5 goes into 75 15 times. 5 goes into 30. 6 times? I guess I could have done a better job. I should have divided them both by 15, shouldn't I? Oh well, it'll still work. Divide them both by 3, you get 5, and you get 2. So that's fine. If you want, raise a decimal, 2.5. 2.5 what? Meters per second. Finished. So again, what's this saying? This is saying that after 1 minute, after this person started walking in this direction, and this person started walking in this direction, 1 minute later, the rate at which they were moving away from each other was 2.5 meters every second. And this will often be the case where you need to draw this second picture once you get to the substitution step. But don't do it too early. Don't do it until after you've done the derivative. Again, that's probably the #1 error. Okay, last one. This is a tough one. A water tank is built in the shape of a circular cone with height 5 meters and diameter 6 meters at the top. Water is being pumped into the tank at a rate of 1.6 meters cubed per minute. Find the rate at which the water level is rising when the water is 2 meters deep. So we have a circular cone. It's going to look something like this. It's not the best drawing, but hopefully you get the idea. And then you have some kind of pump that's spewing water in here, right? The water's coming in like this. And what do we know? We know that the water is coming in at a rate of 1.6 meters cubed per minute. So that's a volume, right? So let's call this dV dt. The volume that's coming in is 1.6 meters cubed per minute. And what we want to know is we want to know about the water level, right? Because this is coming in, the water's coming in, and we got a certain water level, and obviously it's going up and up and up, and we want to know at what rate it's going up. So let's call that the height. We want to know dH dt. Okay, at first it might seem like, well, this isn't too bad. This is like the first question. We're just going to use the formula for the volume of a cone. Now, you might not remember the formula, but I can give you that to you on a test or something. That's fine. So the formula for the volume of a cone is 1/3 pi r squared h. And you might be feeling pretty confident about this. Great, let's just take the derivative. But hold on a second. Look on the right-hand side here. How many unknowns are there? There's actually 2. You have the r and you also have the h. And you don't want to have 2 unknowns. Maybe I'll even just write that in there. You don't want 2 unknowns here. Or if you want, you don't want 3 total. You've got the v you don't know, the r and the h. So this is not good to have the r and the h. It'd be nice if we could write one in terms of the other. That's actually what you're going to do here. So what we're going to do is we're going to take a look at some of the information they give us. They tell us, for example, that the cone has a height of 5. So from here down, that's equal to 5. Oh, sorry, that's 5. And it also tells us the diameter is 6, or that could help us with the radius, right? Now, if you take a look at what I've drawn, I'm going to draw this, it makes a triangle here, this black triangle. I'm going to draw that black triangle down here. And I'm also going to include this line right here. Because what you have here is similar triangles. It's not something we stress much in high school math, but we should. It's a very powerful relationship when you have similar triangles. So I'm going to label in this drawing here everything we know. First of all, if we look at our water level, the water level here, this is all water, right? This is all water. And why don't we call from the bottom to the water level, let's call that h. That's what it is, it's the height. And why don't we call from here to here, why don't we call that the radius of the water? Because obviously there's the whole diameter, this is the radius of the water. That's the small triangle. But if you look at the big triangle, you also know some facts. You know from here to here is how much? Well, that's half the diameter. It says the diameter is 6, so this is 3. And if you look at this whole side of the big triangle here, how much is that? That is 5. It tells us that the height of this thing is 5. So what we have is a right angle triangle. We actually have 2 triangles. We have the big triangle and we have this small triangle here that's now colored in blue, and they're similar to each other. They both have right angle here, they both have the same angle here, they share the same angle here, and because of that, their third angles have to also be the same. They're similar to each other. So what that means you can do is you can set up ratios. The ratio, for example, if we look at the big triangle, the ratio of 3 to 5 has to be equal to, so this side to this side in the big triangle has to be equal to what in the small one? R to H in the small one. And now what we should do is we should solve. Either solve for H or solve for R. And the one you solve for is actually that letter will disappear once you substitute into this. So if you look, what we're eventually interested in is H. We're interested in height. So what I would do is I would solve for R here, because then when we substitute into the R, we'll just have H's left, which is exactly what we want. So let's solve for R. The way you could do that is cross multiplying, or if you want to be more mathematical about it, multiply both sides by the common denominator. What's the common denominator? 5H. So I'll multiply this by 5H, multiply this by 5H. When I multiply this side by 5H, the 5's that cancel, I'm left with 3H. I know some of you are like, why are you doing that? Just cross multiply. But I've had it ingrained into me by other math teachers, I shouldn't cross multiply. On this side, the H's cancel, I'm left with 5R. And remember which one I said we should probably solve for? R. So let's divide both sides by 5. I get R equals 3H over 5. Great. The reason that's very useful is because now if I go back to this, I can plug into the R 3H plus 5, sorry, 3H over 5 squared, don't forget the squared, times H. That H is still there. I know it looks more complicated, but the good thing about it is we only have one unknown letter on this side now, just the H. So you're going to have to spread the love here. This 2 goes to the 3, the H, and the 5. So what's that give us? That gives us 9 H squared over 25 times H. We can keep simplifying. On the top we have 9 H cubed, right, and a pi. So let's put 9 pi H cubed. On the bottom we have 3 and 25. 3 times 25 is 75. But wait a minute, we could actually cancel out from the 975. We could divide them both by 3. So this would be a 3, this would be a 25. Which means what we're left with is 3 pi H cubed over 25. Awesome. So what are we going to do now? All we've done now so far is just found the equation that relates volume and height. The next thing to do is to take the derivative. So let's do that. We take the derivative of this side, and what you get is dv dt equals, okay, on this side, there's only one unknown amount here, and that's this H here. So what we're going to do is we're going to take the derivative here. Power rule says the 3 comes down and multiplies the 3 here. So you have 9 pi over 25, that just stays the same, and the H cubed goes to H squared. And because we're doing implicit here, this is in terms of t, it should be dH dt. Good, now we're able to start plugging in. Do we know dV dt? Yeah, we do. It's 1.6. This we know, 9 pi is just a number, 25 is just a number. H, do we know H? Yeah, but you're not looking for here for it, you're looking up here. It says, find the rate at which the water level is rising when the water is 2 meters deep. So we are going to put 2 right here. Notice I didn't plug 2 in here. Again, that's where people get into trouble. When they draw this drawing, they put a 2 in at this point. No, you're saving that until the end. So we have 2 squared, and then dH dt. Do I know that? That's what I'm trying to figure out, right? So dH dt right here. Just need to isolate the dH dt, and I'll be done. So I have 1.6. This is ugly because I have decimals and fractions. I have 2 squared is 4. Times 9 is 36 pi over 25, and then dH dt. So the next thing I'd probably do is multiply both sides by 25. 25 times 1.6 is 40, so I get 40 equals 36 pi dH dt. Divide both sides by 36 pi, I get dH dt equals 40 over 36 pi. But we could divide top and bottom here by 4, so I get 10 over 9 pi. there's my answer. If you're not comfortable with 10 over 9 pi, although I really would like you to get into the habit of putting these exact answers, but if you're having troubles picturing that, we could take our calculator, go 10 divided by 9 pi, you'll get 0.4. 0.4 what? It must be some rate in terms of time. We want to know at what rate is the water level rising. Well, when you measure a height of a water level, it would be in meters in this case. So it would be meters per minute would be our unit. Okay, again, makes sense what we've just answered here? We've found that as this water is being pumped in at this rate, 1.6 meters cubed per minute, exactly at the point when the water level is 2 meters, at that point, the height of the water is going up at 0.4 meters per minute. This is tough stuff, people. We'll definitely work on this in class for probably a couple of days, and you're going to struggle with this, but you can get it. Believe in yourself.
Yeah.